In the last podcast, we answered questions about the growth and decay of substances using mathematical models that were provided to us in the problem. In this podcast, we're going to be making our own mathematical models. In the case of exponential growth, making the mathematical models consists of coming up with numbers for A0 and for K. Well, A0 is normally given to you as given information in the problem, so it really comes down to finding a value for K. To see how that's done, let's just start right up. Example 1. In the year 2000, the population of Palestinians near Israel was 3.2 million. It is estimated that this population will grow to 12 million by the year 2050. Make a mathematical model for this growth. Now our base year is 2000. That's when time is 0. So in 2050, time will be 50. Now when time is 50, the population, it says, will be 12 million. So that's going to say A is going to be 12. We already know that A0 is 3.2. That's given information. In 2000, the population was 3.2 million. Well, there's a value for T, A, and A0. That's everything that's a variable here except for K. Of course, E is just a constant. So let's go ahead and plug these in, and that should give us K. So A, 12, of course that means 12 million, is equal to A0, 3.2, which means 3.2 million, E to the K, which is what we're looking for, so we don't have any number to put in there, and T is not 5, T is 50, because we're talking about the span from 20 to 2050. So T is 50. Okay, to solve that, we have two steps. We want to isolate our exponential, so we'll have 12 over 3.2 is equal to E to the 50K. Of course, that's just the commutative property on top. And then we want to take logs of both sides. Now, since the base here is E, I'm going to use the log base E for my log of both sides. So I'll say ln of 12 over, and that should be 3.2. 3.2 is equal to the ln of E to the 50K. Well, we've run into this before. Ln and E are inverses of each other. In other words, this is saying the exponent of E that gives you E to the 50K. Well, that's just 50K. Or another way of thinking of it is the Ln and E are inverses of each other, so they just basically reverse each other, and you end up with a 50K. Which means that K is going to be equal to the Ln of 12 over 3.2 divided by 50. Well, that's kind of a cumbersome thing. So what I'm going to do is I'm just going to convert that to a decimal, and I'm going to use that for my math model. When you convert that to a decimal, you write it out like this. Ln 12 over 3.2 divided by 50, and you hit enter in your calculator, and that calculator will give you a 10 or 12 digit number. I'm going to keep a few of them here. I'm going to keep a lot of them because you need a lot of accuracy when you're working with these exponentials. Keep 0.02643512. Boy, that's a lot of digits, but you need a lot of digits when you're working with exponentials. So the first part of the problem said write your math model. So here is our math model. Math model. A equals A0 E, and now I know my K, this is my K, to the 0.024512 T. And now that I've got my math model, I can answer the second question. When will the population be 9 million? Well, at least I can find out how many years it will be. I can add that to 2000, and that will tell me when. So if the population is going to be 9 million, A is going to be 9. A0, of course, is what you started with, so that's still 3.2 E to the 0.02435512 T. And first you isolate your exponential, so you get 9 over 3.2. On the other side you get E to the 0.02435512 T. And of course if I take ln of both sides, which I'll do by just moving the equal sign over here and saying ln of this side and ln of this side. Then again, the ln and the e reverse each other, and so I get ln of 9 divided by 3.2, and this is of course just going to be 0.0243512t, so I'll say divided by 0.0243512 will give me t. And if you just put that in your calculator just like that and hit enter, what you end up with is t equals 39.11, which means it's going to take 39.11 years for that population to reach 9 million. Now, we started in the year 2000, so the year will be 2039. Let's go on to the second. The second one is kind of chemistry related. It says the half-life of thorium is 7,340 years. How long will it take for a sample to decay to 15% of the original thorium-229? You will need a math model. To do this one, you need to know what half-life means. Half-life means in 7,340 years, the amount you have, A, will be half of what you started with, A naught. And we can use that to find K. So let's go ahead and plug it in. For A, I put half of A naught is equal to A naught E to the K times 7340. That's my T. Now, this time I have A naught on both sides, so I'm going to divide both sides by A naught. And the A naughts disappear on both the left and the right, and I'm left with 1/2 is equal to 7340K. I'm sorry, it's equal to E to the 7340K. So if I take ln of both sides, I'll get ln of 0.5 equals ln of E to the 7340K, which is going to tell me when I do my reversing here and divide by 7340 that K is equal to the ln of 0.5 divided by 7340. Now that's not too complicated. That's not as messy as it was above, so that's what I'm going to use in my math model. I'm going to say my math model is A equals A naught E to the log of 0.5 over 7340 T. And now it knows when will you reach 15% of the original amount. Well, if A goes to 15% of the original amount, it would be 0.15 A naught. So I write for A, 0.15 A naught is equal to A naught E to the log of 0.5 over 7340 T. And again, I'm going to divide both sides by A naught to get rid of my A naughts. So now I'm going to have 0.15 equals E to the log 0.5 over 7340 T. And when I take the ln of both sides, I'm going to end up with, we've done this several times now, so I'll just write what you end up with. ln of 0.15 divided by ln of 0.5 over 7340 is equal to T, and when you divide by a fraction, you invert and multiply. So I'm going to invert that fraction, so I'm going to have 7340 times the log of 0.5 over, times the log of 0.15 over the log of 0.5. And when you punch that into your calculator, and I have to do this fast because I'm running out of time, when you punch that into your calculator, don't forget to bracket the top. There's no bar over the 15 there. When you punch that into your calculator, you come up with 20,089. So it's going to take a little over 20,000 years for the original amount of thorium that was there to decay to just 15% of the original amount. And that concludes our podcast.